Hey guys, I'm Timon from Luminovo. Thanks again to eBot7 for the invitation. It's actually the second time at this meetup. I gave a talk at the last one too, and I think the last time I was the very last speaker. And so my theory is kind of because I kept on talking forever and everyone just wanted to get their beer. This time they put me first, but I'll try to stick to the time. We're from Luminovo. We're a startup also here from Munich. We basically help European businesses solve real-world problems with the help of deep learning, and also build tooling to make it easier to implement deep learning algorithms. And what I want to talk to you about today is actually called population-based training of neural networks. Really quick mention, but most of the slides are not by me, they're by Marlon, one of our deep learning engineers, who's obviously better at making slides than I am. But so the whole talk is basically about just an introduction to a paper, actually. So population-based training of neural networks was a paper from, I think, end of 2017 from DeepMind. And in case you guys either find the talk interesting or not interesting enough and still missing some details, the paper is actually very readable, and there's also a very good blog post. I think that you could probably get all of the same information that I'm going to try to give you guys today from also. And so the whole paper is basically about just a new, clever, and I think pretty intuitive way to do hyperparameter tuning. And so before we dive in, I want to take a quick step back and talk just about the motivation when we're trying to do hyperparameter tuning. And so maybe just that I kind of understand also who's listening. Who here has trained a machine learning model before and had to do hyperparameter tuning? Maybe just a quick show of hands. Most people, perfect. Okay, so then this talk is for you guys. And then you guys probably know yourself also that when we do hyperparameter tuning, there's kind of three things that we care about. We want to be faster, so just in terms of wall clock, like how long I have to wait in front of my machine until I have found the perfect combination of hyperparameters. We want the whole thing to be cheaper. So of course we can throw a lot of compute power at it, but we don't have infinite money. So if we don't spend too many G-Cloud or AWS resources, that would be great. And ideally, we'd also want it to be easier. It's kind of the whole point of hyperparameter tuning is the lazy machine learning or deep learning engineer kind of just saying, okay, I don't want to choose these values perfectly. I kind of just want the machine to find out and not think about it too much. And so this is basically, I guess, where the DeepMind engineers were, and so we're going to pretend that we are really slow, have no money, and are stupid, just like the DeepMind guys. That's basically where they started. And so maybe let's have a quick look at how hyperparameter tuning is often done today. I just run experiments in parallel, and let's have a quick look at kind of this drawing. This is from the DeepMind blog post, actually. We're going to have a few of those, so let's try to understand what's going on here. We have three things: the performance, basically that's the little life bar on top of the head of the little guy, the hyperparameters, and the model. And so here in parallel search, you can see the hyperparameter balls always have the same color, meaning they're constant. Usually, sometimes there's a schedule for the learning rate or something, but they're more or less constants for one experiment that you're running. And as you see, for some of these models, the performance gets really good. So I guess green is good, and red is not so good. And the models change while we're training, right? The weights that we're learning and training somehow. And yeah, some of them work well, and some of the experiments we'll try don't work so well. And basically, if we scale this up a lot, we're pretty sure to find some kind of good hyperparameter setting. And the other way you can also do hyperparameter tuning is just sequential search. So that's usually if I'm actually doing it by hand. So I'm starting one experiment, then I look at the results, then I kind of see, here the loss exploded, so I'm going to choose a lower learning rate or things like this. And there's also automated versions of this, like Bayesian optimization, kind of like automated hyperparameter tuning that is still sequential though. So it's basically usually doing something from, with this hyperparameter setting, I got this confidence and these results. And so based on all the results I got from earlier experiments, I'm now going to choose the next one. So it's like a sequential method of automated hyperparameter tuning. And so if we look at these two two methods and kind of compare them against each other, we'll see that parallel hyperparameter tuning is really fast, right? It basically just takes one time until it takes me to train a method, and if I can parallelize as much as I want, it's always as fast as one training takes. It has high resource consumption, unfortunately, because basically the more experiments I want to try at the same time, the more I have to pay. And it's kind of easy. Like if I just, in theory, if we work for Google or something, have lots of computing resources, we just do really massive parallel search over random search of hyperparameters, and we'll probably find something really good. And on the other hand, we have sequential search, which is slow. I'm doing it sequentially. I'm always looking at the results. I'm picking something, going to the next thing, which of course means it has low resource consumption, because I could do sequential search on just one GPU. But it's kind of hard. Depends on what you do. The automated, if you use Bayesian, it's not so hard because you don't have to do anything. But if you do it by hand, then it's kind of, yeah, you do still have to put a lot of thinking into it. And so the DeepMind guys, they were sitting there and basically saying, why not both? That we want to have a parallel, you get the advantages from the parallel search, but it's still being cheap as the sequential search. And here's another one. The one I looked for Google that I thought was really funny, Hillary or Trump. Why not both? And if we look at the real world, we see today that what most people are doing, what we usually did so far before we started using population-based training, actually is already a combination of both. So the way, I used to train hyperparameters for most of the jobs that I worked so far is usually I was doing something in parallel. I usually started as many experiments at the same time as I had computing resources or money on my cloud computing service to spend. I would let them run, and then every now and then I would probably check in, like look at the results, see where the loss exploded, which hyperparameter tunings were going like really badly, and then maybe I would stop those manually, look at which hyperparameters went well, maybe change the search space a little bit. It was kind of a mix out of this sequential and this hyperparameter search that's looking at these images again. I would kind of see, I would stop the experiments that have really bad performance. I would keep the ones that are already looking pretty good, and I would kind of behave more like the experiments that are running really well. And so population-based training is actually nothing else than exactly this process that's usually done more or less by hand, doing in an automated fashion. So what does this mean? The idea is actually very intuitive. Let me see. Okay, that's slow. In their paper, they basically define like five functions that you as a programmer have to write to implement population-based training. The first one step is just kind of doing a training step. So if you train a CNN, that's just taking some stochastic gradient descent steps. The eval function is just telling what is the performance, what are we actually trying to optimize. So usually that would be the metric that you chose on your validation set, for example. And then what happens is basically that every now and then, every few steps, you would just take a look at all the parallel experiments you started in common. You would then look at which one is performing the best, exploit that information. So one thing you could do is just pick the best model you have right now after, let's say, an hour of training the neural networks. Exploit that steps. That's what's going on here, is that you pick the hyperparameters, the green ball, and the model weights from the best model. Take those, and then the key part of population-based training is then kind of this idea of genetic algorithms that then you do some exploring. Because if you just take the best models, now I would have 5 parallel things that are training the same thing. But what they do basically is that then they say, from this hyperparameter setting, I'll change this up a little bit now. So for example, if it's the learning rate, it could be that you sample again with some noise to the left or the right, or if you have any other kinds of hyperparameters, you could come up with maybe just randomly picking another sample again. But basically, those are the 3 things you have to define. So this ready function means basically how often do I do this step of explore and exploit, exploit and explore. and then the actual exploitation and the exploration. And so then basically what you do then is that you just keep training, and here it's just only done in one step, but usually population-based training basically happens very often. So maybe you would do something like every 10 minutes while you're training, you have a look at which of your models work the best, take those hyperparameters, take those model weights, copy it to all the others, and then do a little bit exploration on those hyperparameters. Any questions so far, maybe? Yeah?
So does it mean that I finish the training first and then tweak hyperparameters automatically, or do I, during training, without having finished on the training data sets, already tweak hyperparameters and change populations?
During training. So you're doing this during training usually, so the way you would choose this ready function, this is basically what's telling you how often do you do this step of tweaking the hyperparameters. Usually you would try to do it based on your computation power or something, that it happens every 5 to 10 minutes or something to be effective. You can choose this however you want. You could do this every once in an hour if you know that it takes for days to train your neural network. If you know it's pretty fast, you could do it every minute or so. Martin?
Would you make a lower bound on the epoch size? So would you tell it to at least run through every sample of your training set once?
Before doing a tweak?
Yes.
You don't have to. I think this very much depends on the data set size that you have. So if it's very small, you probably would want to do that. I think from what I've read online and how we've used it so far, what we mostly do is you actually think in wall clock time. So I'm really thinking just, I want this to happen. I'm going to train, I have like 8 hours, let's say overnight, that I want to train my neural network. And I just want to happen, this process to happen every 10 minutes or so, just so that it happens often enough, because it's actually good if you always kind of exploit what you've done so far, but if you take too little steps, right, then it's basically nothing really happens. And you can't discriminate between good and bad hyperparameters. Yeah?
Is it hard to get reasonable default functions for each of these things? Because it's easy for me to imagine that if these are not trivial to implement, then I've just introduced 5 new really complicated hyperparameters to my training that I didn't have before, right? Mm-hmm. And then I guess as a follow-up, with some default, do I have some kind of guarantee that probably the model that will result from this, isn't going to be worse than if I just straight up tried a few different combinations, let them all finish their training and then pick one? How much more complexity does this actually add?
Right, depends on how fancy you want to get. I would say the default options here are actually pretty easy. When we look at the results, we'll have a few different exploit functions, for example, that they tried. And basically, the one they found in the end is it's not selecting the best model, because that's basically doing too much exploitation. But what they I think usually do is something like when doing the exploit step, copy models from one of the top 20% of models in my population right now. So let's say if I have 10 GPUs and run 10 experiments at the same time, I don't just copy the one from the best, but randomly pick from the best 2 that I have right now. That's my exploit step basically. I take the hyperparameters from there and the model weights. And then the explorer step depends kind of on your hyperparameters. For the learning rate, it's really easy. The default is just something probably sample again from there, or somewhere in the vicinity of somewhere there. And then depending maybe if it's things like you want to change the optimizer from now on, right? You can get as fancy as you want. So if you want to now not use Adam instead of RMS from now on, or something like this, you could also have a choice or something and just randomly take a different one now. Yeah. Okay. Could you guys hear anything that I said before? Maybe that's why there are no more questions. Okay. Okay. Maybe let's have a look at the results, because actually this is the interesting thing to me. So when I first heard about it, I just thought it actually makes a lot of sense, because basically what's happening, it's what I'm doing manually when I'm doing this stop the bad experiments and start new ones that are more like the good experiments. And really, to me, kind of this is all that it is. So it's a very intuitive idea. It's kind of what it is. Stop the bad ones, keep going with the good ones. And so by that, you're basically not wasting computing times. I've had this many times before. I started 10 experiments overnight, and I saw 6 of them. I basically just wasted money because they were super bad right from the beginning, and there was no point. I could have just stopped them right away, but I was asleep. And population-based training does this for you. And yeah, so the results are really nice. I guess that's why they got the papers published. And so I'm sure about the crowd here, I'm actually not a reinforcement learning guy really, and the DeepMind guys are. So I think the first 3-4 examples are with reinforcement learning algorithms, Unreal, A3C, feudal networks, and transformer. But they actually here have two results, one with machine translation and one with GANs, which we'll hear about more later, I think. And they basically showed that for some of these standard problems like Atari, by just using the standard algorithm that was published in another paper and just using better hyperparameter tuning, namely their hyperparameter tuning, they get better results. And so when I read the paper, I thought that's really cool because basically you don't have to do much. You have to implement this thing once, but then from then on you usually kind of are guaranteed, maybe not guaranteed, but very likely to find better results and to do good hyperparameter tuning.
Sorry, what's the y-axis? Human optimized performance?
It depends kind of, these are reinforcement learning games, so this is like Atari, for example. These are like the computer games, and so I think this is in regard to human performance. So the humans usually get for this one Atari game score 50, and so this reinforcement learning algorithm then got score almost 100 or something. I think that's what it means. So here are some kind of like parameters of things they try to just get a little bit of a feeling where population-based training works. And I think in theory, right, you guys could try many, many more things with this, maybe publish a new paper and find even a better method. So one thing they played around with is just the population size, right? And so there they see that starting from maybe 20, at least for what they tried, the results are probably too marginal to be worth the money to buy so many more GPUs. The exploiter, I think that was your question, Philip. Here's basically two different methods that they tried, and the difference is not huge, but a little bit. And so truncation is basically the one I already described, the kind of intuitive one. You just pick one of the top models and copy that one. And binary tournament is actually way more complicated method, and I'm glad it performs worse, so then you don't have to remember it every time. It basically works that every model randomly chooses another model and then basically flips a coin if it either keeps its own or takes the other one. So it's kind of a very random method, and it didn't work better. I actually might have gotten that one wrong. Better read it up, but it's worse, so that's why you don't really have to remember how it works. And the other one that's, for example, interesting, they also tried just copying the hyperparameters or just copying the weights and not both, but found that it's actually important to really benefit from everything is that you really take both. So when you do the exploit, you exploit the hyperparameters and the weights that have already been trained, because you basically have a model that's much better than the one you have right now, and you might as well make use of that. And then the last maybe interesting thing to understand about population-based training, I think I have it on the summary slide too, is so the one thing that's maybe a little bit unintuitive that really changes when you use population-based training, when it comes also to reproducibility, is that usually when you run these parallel search experiments with like one set of hyperparameters, maybe a learning rate schedule that you defined beforehand, you just run it with that, right? And I could run it exactly that one again, and it would be very easy to implement to get the same results. But here, we now actually have adaptive hyperparameters, so to speak, right? Because by doing this exploit and explore, the model that I have in the very end, that's my best model, will actually have seen many different sets of hyperparameters throughout its life, right? And so that's a little bit unintuitive. I guess it's up to you to decide if this is important, if this is a disadvantage or not. It would basically mean you have to like run the whole experiment with the same random seed, or really complicatedly implement the changing of hyperparameters without actually doing population-based training in parallel. But what they showed basically is that this adaptivity is actually very important and makes a big difference in performance. And the other thing, the final top 3, that's much worse here in the improvement over their normalized baseline, is that they took the very final hyperparameter set they got basically at the very end from the best performing model and used this fixed hyperparameter set to train it from the very beginning and to just see if it's maybe population-based training is just a way to find the right hyperparameters that you should be using. But that's not the case, so the real benefit comes from this adaptivity of learning rates and schedules. Okay. Questions so far, now that you could hear what I was actually saying? None, then I will move on and show you a really cool visualization that was of course not done by me, but by the DeepMind guys. And so let's have a look at it for a few seconds maybe to understand what's going on. I think so the color code at the bottom, this is the score, like so the performance of the model in some sense. On the right it's reinforcement learning again, so it's the cumulative expected reward. And so the bluer it gets, the better the model is basically. And what you just see here is that you have a population that starts at the beginning, and then what happens, right, every few steps we basically copy and take the best model we have so far and keep exploring from there. And so you see by that you get bluer and bluer, which means your model is getting better and better. And I guess there's not a big point to it other than that's a really fun visualization. And visualizations are awesome, and then you feel like you even understood it better than before. Yeah, so takeaways. It's still fast, right? It's exactly as fast as parallel search was before. So if I start 10 machines and overnight, it will still take me the same time than if I would have just used fixed hyperparameters. The resource consumption is still high in the sense that I'm still using 8 GPUs, but it's actually much lower than parallel search because I'm getting better results faster, right? Basically with one run, I don't have to do this parallel, then sequential, pick some new things, parallel again, pick some new things, parallel again, but it's basically done for you in one run. And it's much easier. So one thing that I'm super happy about is that one of the things I always hated tuning the most was this damn learning rate schedule, because it always had a pretty big impact on how well your models are, and then sometimes it's a little bit too high and you see, I need to now load the checkpoint from there to change the learning rate a little bit to get a little bit more performance out of it. And with this, you don't have to do any of this anymore, right? The learning rate is adaptive through the method of the population-based training. So you have none more of that. And one of the things they also mention in the paper, that especially if you have new hyperparameters, so if you're doing research and you're coming up with a new method and you have some new hyperparameter that you've never seen before, where it's maybe not as easy as just taking the learning rate that the guys took in the paper that you're trying to reproduce, then this is actually a great method, right? Because you have to know very little about it. You just take the bounds and kind of the population will figure out for you what the best schedule for this hyperparameter is. And then so maybe the best news for all of those that are actually doing machine learning in the wild and applying it in their everyday lives. This is actually implemented already. So there's a really cool project from the University of Berkeley in California called Ray. That's under very active development. So it's actually still pretty unstable. But it has this implemented out of the box. And so it's kind of as easy as following their interface to run exactly this population-based training for your hyperparameter tuning. So if you want, you can just go try it out for the next time you train a deep learning model. And I think that's it. We still have a little bit of time for questions, I think. Thank you very much.